So with the introduction into what was the motivation, for what we did and what we learned so far, it gives us a good segue to look at the state of our tuning currently. So for machine learning methods, outside of those that we covered in this course, there are a few more other branches that hopefully can be covered in a more advanced course later on. But basically it falls into, roughly speaking, three main categories. So we covered deep or convolutional networks in this course, although you don't really need a deep network to do most exercises we ask you to do. And those are the sort of supervised classification tasks that you need at some stage of your tuning, and you want to embed the result of that classification or a feature identification into your whole tuning routine. There is super many different flavors of this at the different tuning levels, and this is something that's being pretty successful. And currently the question of solving a higher dimensional problem feels more like a question of technical progress than fundamental challenges. Another field or a subfield is that of application of reinforcement learning in tuning challenges. So reinforcement learning works fundamentally a little bit different from the type of learning that we discussed in this course. Specifically, the feedback loop is already embedded in a learning algorithm, as in there is an agent who makes a decision about what to do next. You don't have to just train a supervised learning and then have a Python decision loop around it. The reinforcement learning immediately gives you feedback. This feels like this could be then a great candidate for any kind of tuning experiments, because you don't have to think about the feedback for yourself. And sometimes it is. The challenge is that for the reinforcement learning, you need to be able to have a reward that is easy to evaluate. And you also need to have access to the larger amounts of data, because of this extra feedback stuff, these algorithms are usually more expensive to train. Roughly, you need order of magnitude more data compared to the deep networks. So this then creates some kind of machine learning challenge then that one should have in mind, especially when it comes to easily evaluated reward. It's not always the case in a quantum experiment. Sometimes you have to simulate something very hard, or you need to measure something very expensive. But there are cases where it has been used successfully. This is a very nice paper from Natalia Ares group from 2021, where they indeed used reinforcement learning for a tuning task. Another general broader field that I want to mention and that I am personally super excited about is that of generative models. We saw example of a generative model in this course already, and that was in the module 3, where we created this autoencoder and asked it to reproduce a charge stability diagrams, and then we learned that the latent space actually sort of automatically learned to classify which charge stability diagram is in which quantum dot regime. This general spirit translates into the whole array of other generative model. The example that you see here is from our paper this year, where we tuned a complicated topological mode of semiconductor superconductor quantum device using a generative adversarial model that learned to reproduce the data measured on the experiment. And while it learned that, it sort of, as an afterthought, figured out how to determine the Hamiltonian parameters really precisely. And knowing these Hamiltonian parameters was extremely helpful in tuning of these hybrid semiconductor superconductor quantum devices. These generative models are also more expensive and sometimes unstable to train. But there is so much diversity in the kind of architectures and loss functions you can try, and especially the potential of extract information from these latent space representation is really rich. So for me, this is something that I am super excited about. You see that this work is really from 2023, which is when we are recording this course. So this is something that is happening just now, and I expect there is going to be a lot of exciting progress in a generative model subfield going forward. So overall, one can say that machine learning is becoming more and more important for tuning quantum devices, especially when you take into account supervised tasks. There are algorithms now that perform at least as fast as an experienced expert. So now the experienced expert can do something else with her day. What we show, however, so far is the representation of the success on a sort of still smallish devices with a few parameters problem. Enlarging these parameter spaces is a really active effort currently. So if I would have to formulate a key challenge in the field right now, it would be doing fully automated large-scale tuning of chips that have 15 or more qubits. And that would mean regime tuning, charge tuning, and maybe even fine-tuning, a full pipeline of tuning that is for an expert human operator a fully hands-off. This is an ambitious challenge, but with the progress that we are making so far, I think not completely unrealistic to see this within the next few years.